Okay, so we are re-recording today's lecture. Right now it's Wednesday the 13th. The lecture in class crashed again, so I'm going to do a new recording software so I don't have to keep doing this. We finished up with age hardening mechanisms. And so today and Friday, we're going to look at strengthening mechanisms for aluminum alloys other than age hardening. And then next week, before our exam on the 29th, we will finish up with a bunch of specific commercially relevant alloys and how they're processed and how they're used. Okay. So we talked about strengthening mechanisms in the first lecture for solid solution strengthening, solid solution hardening. And I put a bunch of text here because this was something that a lot of the class expressed some confusion about, and the reading may not have been. It's sort of a difficult subject, right? So I've given some reading in Courtney, which I think is one of the best descriptions, but I've cut and pasted some points out of the notes from Professor Frazier when he taught this course here on solid solution strengthening, and his notes may make a little more sense to some of you. Some of you may find them more confusing. Personally, I think the Courtney reading is much clearer. But just in case it's helpful for you, it's here. The main points that I want to get to stress, right, and the main points that are going to be hit on the exam is there's two effects when we consider solid solution strengthening. We have to consider the size effect, right, which is that a solute atom that is different in size than the matrix, the parent metal, is going to cause a strain field. And that strain field is going to interact with dislocations and make it harder for them to move. The other effect is the modulus effect, right? The dislocation, line tension, right, or the energy of the dislocation, we can say, GB squared, right? So anything we do to change the elastic modulus of our material, or the shear modulus, is going to affect the energy of the dislocations, right, and make it more difficult to move, right? So those are the big things to keep in mind for solid solution strengthening. And remember that in FCC metals, we need to consider how strong of an obstacle the solute atoms pose. So if we just consider the size effect for a second, right, remember that the strain field for a screw dislocation is pure shear, so it doesn't have a hydrostatic component. So dislocations that are pure screws don't care about the strain field around a mismatch. They do care about the modulus. Edge dislocations, or dislocations with an edge character, do have an interaction from the size effect, right? And then in BCC, we have to consider that interstitials in BCC give a very large distortion that is not spherical, it's not purely hydrostatic, and that gives a very strong interaction, right? This is what gives the high strength to carbon and iron, and nitrogen and niobium. And so these will be important for later alloys. But for right now, right, when we're just talking about aluminum, the amount of strengthening that you get from the substitutional solid solution is fairly modest compared to carbon and iron, right? But it is a very important effect, and we'll see when we aluminum lithium alloys that you get a pretty significant strength boost out of just the substitutional solid part. Okay, now, as I had mentioned in class, I wanted to go back and talk about a couple dislocation interactions that I think are important, and I had assumed previously that you saw these in the defect class and that I wouldn't have to cover them. But since I've learned that for some of you, this may be the first time you're seeing it, so we're going to go back and talk about two really important dislocation mechanisms, interactions, jog formation and dipoles. Okay, and so let's consider an experiment here where we have a edge dislocation going from A to B, a screw dislocation from C to D, right? And this edge dislocation is moving in this plane along this direction, right? So the edge dislocations, remember, the Burger's vector is perpendicular to the line direction, and the dislocation moves in a perpendicular direction to the Burger's, a parallel direction to the Burger's vector, right? And so when it hits this screw dislocation, something, right, they're going to interact. They're going to have a reaction, right? And most importantly, they're going to form a jog. So a jog is basically becomes a step in the dislocation. And when two dislocations interact, they form jogs. And the step, the direction of the jog is in the Burger's vector of the dislocation that it interacted with. So this edge dislocation now has a step. It leaves this plane, right? This was the original slip plane. Part of the dislocation now has a jog and is in this plane here. Now, the Burger's vector has to be the same across the entire dislocation line length. But if we see the jogged region doesn't lie on the main slip plane anymore. It now lies on this plane PQRS, right? Which means this is going to cause some hindrance to the motion of this edge dislocation, right? The edge dislocation here is still free to move on this plane, right? This is a valid slip plane for this dislocation in this configuration because the Burger's vector still lies in the slip plane, right? And we can still move in a direction that's perpendicular to the line length and parallel to the Burger's vector. So this is a perfectly fine plane for this to move on. But remember what the driving force for the dislocation is, right? It's the stress in our material, the resolved shear stress. So it's the stress projected on the slip plane along the slip direction or along the Burger's vector direction, right? And this comes from our Schmidt law. We have two angles in there, cosine phi and cosine theta, right? One angle for the slip direction, one angle for the slip plane normal. So this plane here, our original slip plane, and this smaller jog slip plane, PQRS, are likely to have different resolved shear stresses, right? And if our stress is well aligned to move this dislocation on this plane, it's likely not well aligned to move this dislocation, this jogged section, on this slip plane. So this jog we'll basically have to drag this jog along, right? And that provides some modest impediment to the motion of this edge dislocation. Now we have to consider the other case. What if we now have two screw dislocations interacting here? right? Remember, the dislocation still moves perpendicular to the dislocation line. In this case, the Burger's vector of a screw dislocation is along the line length, right? And so the dislocation moves perpendicular to the Burger's vector for a screw dislocation. We get our jog. So our dislocation again leaves the slip plane, right? We now have a step. We go from one plane to the other, right? And now if we consider, we now have this step here, the dislocation, right? Our Burger's vector is up, right? We need to conserve our Burger's vector across the entire line length, right? And the Burger's vector can only move perpendicular to its plane, right? So this dislocation is essentially sessile now, this jog region. It can't move in the same direction as the rest of the dislocation. It can only move in this plane here defined by PQRS. So what happens is this dislocation here is going to bow out, right? While this is stuck, right? If the stress state is right, this can run along, right? And catch up, but chances are that this is now essentially a sessile dislocation, right? This is an extreme impediment to dislocation motion, right? We call these dislocations that run through the slip plane like this, that are vertical through the slip plane. The general term for these we call forest dislocations, and we call this mechanism of these dislocations interacting with the forest dislocations and creating jogs, forest hardening. It's the general term. So if you hear the word forest hardening, this is what we're talking about. But any dislocation that has a screw component, which means the screw part of a dislocation loop or partials, we're going to have a significant impediment to motion from jog formation. The other mechanism that I want to stress is dipole formation. So imagine now we have two sources, one out here and one off the screen this way, and they're pumping out dislocations of opposite signs. So these dislocations, here's the source. These dislocations are coming this way. Here's the other source. These dislocations are coming this way, right? So if these sources were on the same slip plane, these dislocations are of opposite sign, right? So they would just be attracted and annihilate and disappear. However, if they're not on the same plane, they're separated by a distance, the planes that they're operating on are separated by a distance y, what's going to happen is dislocation B moves in, right? Remember the stress field around an edge dislocation, right? It changes sign depending on which quadrant you're in, right? Basically, we have, if a dislocation is out here, let's say this one, as B comes out of the source, it's going to feel an attraction, right? Until it gets to a distance x, which is exactly the same as y, right? So when it's the same distance to the right of dislocation A that it is in the x direction, the vertical direction, the y direction from dislocation A. So when this is a 45, 90 triangle, in other words, the force on this dislocation is 0. It's neither attracted to A or repelled from A. But if I try and drive it closer, now it's repulsed until it comes back, right? There's a force on this dislocation trying to push it away. Until, of course, I get perfectly aligned. Then it'll snap over to X again here, but then it's interacting with these other dislocations, so it becomes a little more complicated. But, right, as we come up, we have a force that's pulling it to a distance X equals Y, and then it will repel it back this way, right? And this is called a dipole, right? It's these dislocations that are their elastic stress fields are, it's such a configuration that they're not exerting any force, but to move them farther away will give them an attractive force. To move them closer will give you a repulsive force. So it's this analogy of these two dislocations are sort of like in a stable bond, right? Sort of like a chemical bond. They're going to try and return to this equilibrium spacing, right? And the closer this plane is here, the stronger this effect, right? The force goes by 1 over this distance. Okay, so that's dipole formation. So those are two important dislocation interactions that give rise to work hardening, right? Remember that dislocations are obstacles to other dislocations, and we need to consider the specific mechanisms of interaction. And when we talk about work hardening, I didn't point out the dislocation, these specific mechanisms, because I thought you would be intimately familiar with them. Okay, so grain boundary strengthening in aluminum alloys. Well, let's talk about FCC alloys in general, right? Remember the Hall-Petch coefficient, that the yield strength grows by the square root, 1 over the square root of the grain size, right? But we see that the grains, the effect for FCC metals is significantly smaller than that of BCC or HCP metals, right? So why is that? Right? So basically the answer is in the slip systems, right? What are the slip systems for FCC, right? Are the 111 planes along the 110 direction, right? So we've got 12 slip systems, 12 degenerate slip systems. They all are equivalent. They have the same energy. And they tend to be fairly easy to activate, right? Remember, we're slipping on a close packed plane along a close packed direction. If we consider BCC, we're going along the 111 direction on the 110 planes, right? So this is not close packed planes, right? And we can also go in the 111 direction on the 112 plane and the 123 plane, right? So we've got slip systems that are not necessarily they're not degenerate, right? They're all different slip planes. They exhibit a large range of critically resolved shear stresses, right? The 110 systems are significantly easier to operate than 112 or 123, right? And so because they have more slip systems and they're not close packed, we have many different types of dislocations, right? And they give us very strong locking mechanisms, right? So what does that have to do with grain boundary strengthening? Well, remember, what's the mechanism for grain boundary strengthening, right? We have a polycrystal. So this grain is favorably oriented for slip. So we have a dislocation source here. It's pumping out dislocations. The dislocations come to this grain boundary. They can't cross. Why can't they cross? Well, because this grain, the slip systems on this grain are not really well aligned with the ones for this grain, right? So that means the dislocations have to change planes. They enter the grain boundary. There's always debris left over. They have interactions with the grain boundary dislocations, right? It's a messy situation, right? You can get 90% there if you just think that the slip planes and slip directions in grain A are not well aligned with the slip planes and slip directions in grain B. So what happens? They pile up, right? So this dislocation pile up at the grain boundary gives us a stress concentration, right? That stress concentration eventually gets large enough to activate a source in grain 2 here, right? So in FCC, this source is we know it's sitting on a 110-111 type slip plane, which we know is easy to activate. If this is BCC, this source might be on a slip plane that is very difficult to activate, right? And then because of the interactions, I may not be able to get nearly the degree of pileup at the grain boundary, right? So that's why FCC in general has a rather weak Hall-Petch effect relative to BCC and HCP. Okay, and then we'll show that aluminum itself, when we talk about microstructure effects in just a little bit, we'll discuss that aluminum actually has a significantly a very low Hall-Petch coefficient. Okay, so an important thing, if we're going to try and take advantage of grain size effects on strengthening, right, we have to be able to first achieve a small grain size by processing. Then we have to be able to keep the grain size from growing. Well, how do we do that? How do we refine the grain size? Right? Well, we can do that by recrystallization, either dynamic recrystallization during hot working, or recrystallizing by cold working and then annealing, or static recrystallization. A lot of FCC metals undergo dynamic recrystallization quite readily. Nickel, for example, copper, right? So low to moderate stacking fault FCC metals will dynamically recrystallize quite readily. Aluminum, on the other hand, and other high stacking fault FCC metals do not dynamically recrystallize very easily. However, they will undergo static recrystallization when pure at very low temperatures. Okay, so we know by thermomechanical processing we can obtain a small grain size. How do we keep that grain size? Well, we're going to use a mechanism, basically particle pinning, right? So what's the driving force for grain growth, right? So in recrystallization, we're talking about a balance between the stored energy in terms of the elevated dislocation content and the surface energy of the new grains, right? You're going to nucleate new grains to eliminate the stored energy, gobble up those dislocations, and leave behind a nice clean crystal lattice, right? But then now we've got a bunch of small grains. We have a lot of grain boundary energy, right? If we can grow those grains and eliminate grain boundary area, right, we can further reduce the energy of our system. Okay, so we can pin those grain boundaries by considering particles, right? If we have a very fine dispersion of particles, so how can we do that, right? The first thing we need to consider is that we want the interfacial energy of the particle matrix to be very low, right? In fact, we want it to be much lower than the grain boundary energy, right? So imagine if we have a grain boundary that moves forward, and now we have a whole bunch of particles sitting on that grain boundary. If the interfacial energy is lower, right, the matrix atoms would rather be touching the particle than the grain boundary. So essentially, you can replace portions of the grain boundary by the particles, right? Then if you move away, you're increasing the energy because now you have more matrix touching the grain boundary, right? And so this is a very good mechanism for pinning the grain boundary, right? And luckily for aluminum, unlike some other metals, we always have a number of impurities in our aluminum that will exhibit very low interfacial energies, right? Titanium, here say titanium, chrome, nickel, but we also have to consider strontium, silicon, iron, right? And then the other thing we have to consider is we don't want to make very large particles at the grain boundary, right? Because these give us problems when we have the stress field due to pileups, right? These large particles tend to be brittle, right? And they fracture, they crack, right? We'll talk about that more in just a little bit. So what we really want is a dispersion of submicron particles. Okay. So large coarse intermetallics in the microstructure, right? These tend to be very brittle, right? If dislocations pile up on these particles, the stress concentration is going to fracture the intermetallics, right? So we always consider these as unwanted, right? And for structural alloys, a lot of processing is to prevent these intermetallic particles from forming. However, in applications where cost is the main priority and the mechanical properties are fairly modest, things like window frames, right? All through Watts Hall, all the window frames are aluminum, right? Their presence can be tolerated because they're not under large static or fatigue loads. Okay. So we had solid solution strengthening, we had cold working, we have grain boundary strengthening, and now another strengthening mechanism that we need to consider is texture, right? So crystallographic texture some of you probably haven't heard of before, right? But it's the preferred crystallographic orientation, right? We've got a polycrystal. If I have a powder metallurgy alloy, I start with a powder, right? And those particles are all jumbled up, right? There's no orientation to those particles. When I sinter it, I'm likely to get a random distribution of lattice orientations, right? They're all going to be pointing in different directions, and they're going to be all mixed up. Same thing from most solidification processes, right? If I just pour into a mold and then I cut a sample out from the center of that mold, right? We'll ignore edge effects, right? It's going to be large grained and fairly random, right? Because I'm nucleating grains in the liquid, and there's no preferred orientation unless there's like directional solidification or something. But there's no preferred orientation for how that those grains are going to nucleate. However, if I then deform those samples, right, the grains rotate during deformation, right? They will tend to rotate towards certain stable orientations for the loading condition that they are under: tension, compression, shear, biaxial, deformation, right? And remember, some grains are well oriented for slip and some are less favorable orientation. So some grains are going to deform and others are going to resist the shape changes, right? So they're not deforming in the same way. And this heterogeneity of deformation leads to some orientations being more preferred, right, appearing more frequently in the sample than others. So this is a pole figure for a FCC rolling texture, and we're looking here at the directions of the 111 plane. This is the stereographic projection, right? So the probability of finding this 111 planes in these directions are much higher. This is the rolling direction here. This is the transverse direction, and this is the direction coming normal out of the rolled sheet, right? So what we see is we have a much higher probability of 111 plane normals pointing along the rolling direction and at about 45 degrees away from the normal direction of our sheet, right? And we have a very low probability of finding grains that are intermediate, where the 111 is intermediate, about 60 degrees between those two directions. Okay, so what causes texturing? Right, remember back to mechanical behavior, right? Remember if you do a single crystal tension test, right? You get slip lines, right? But this, if I have slip this way, this grip wants to move this way, right? But it's constrained by my tensile frame, right? So in order to conform to the constraint, this crystal has to rotate, right? The same thing under compression. So when we deform something in tension, the slip direction rotates towards the tensile axis. The slip plane normal rotates away from the tensile axis. Compression is the exact opposite. We have the slip plane normal rotates towards the compression axis, right? In polycrystals, the deforming grains, a grain that's deforming has to stay coherent with its neighbors, right? And so that's a powerful constraint on the grain, right? And we're going to have rotation. The other effect is that anytime we have gradients in deformation across the grain, that's going to give us lattice curvature, right? Whenever we have a strain gradient, we develop a curvature of the lattice, right? And all these effects go into texturing, right? Leading leading to preferential orientations as a result of processing. Okay, so we're almost through. So I want to look at some, going back to aluminum alloys, I want to look at some microstructural features, right? So the first microstructural feature that we want to consider is coarse intermetallic compounds, right? Particles. So I'm talking in the range of 1 to 10 microns, right? This is going to, they form during solidification or processing, right? Iron and silicon are very hard to get out of aluminum, and they tend to be there, right? And so you end up with, we have a suite of insoluble particles, which means that there's no solvus for these in the solid state, right? You have to go up to the melt before these will dissolve, right? And some of them are quite difficult to get out. This is a real challenge with recycling aluminum. And we have soluble particles, right, which are basically our precipitation hardening good guys: copper, aluminum, magnesium, silicon, right? Now, after deformation, these intermetallic compounds tend to be aligned in stringers. So in class today, the question was asked about the mechanism. Well, remember, these are, the grain structure starts out equiaxed, right? And these particles tend to be at the grain boundaries. They tend to nucleate heterogeneously. They're at the grain boundaries. But then we might have a 90% or a 95% rolling reduction. So those grains become really elongated, right? So nice equiax grain now becomes these really long pancakes. Basically, all of the grain boundary area becomes aligned like this, right? And so this is why these intermetallic grain-bound compounds tend to become stringers, okay? Right? And then we have a second range of intermetallics, right? These are submicron dispersions, some say 50 to 500 nanometers, right? And these are the particles that help retard recrystallization and grain growth, right? So these are our good grain boundary pinning particles. And then fine precipitates, right? These are the ones, right, on the order of nanometers, right? These are the ones that form during age hardening. These are the good guys, right? Right. And remember, these coarse intermetallics are brittle, right? So they give us opportunities for cracking and fracture. Okay. Grain sign and shape is quite important to the properties of the aluminum alloy. Dislocation substructure, right? Remember, we talked about low energy dislocation structures that form during working operations, right? Dislocations tend to form dislocation cells, where the dislocations are packed into the cell walls with the largely dislocation-free center of those cells. So let's consider, these are the microstructure features. What about the specific effects on the properties? Okay. So remember, we've got two types of alloys that we want to consider, right? Heat treatable alloys, right? So we got the very finely dispersed particles that give rise to strength. And the non-heat treatable alloys, right? Where other strengthening mechanisms alloys, right? That we need to exploit all the mechanisms that we talked about today, right? And the emphasis is going to be on working these is how can we get low-cost approaches to strengthening, right? Okay, so our first thing that we want to consider is coarse intermetallics. Very little effect on strength, right? I'll even say no effect on strength. However, they strongly decrease the ductility, right? These can crack at small strains, leading to internal voids, right? So remember, these form into stringers, right? Here's a cube, right? And so we have three directions. We have longitudinal to the stringers, transverse to the stringers, and then short transverse, right? And each of these directions, the presence of these stringers of intermetallics is going to give us a strong degree of anisotropy in the mechanical properties. So if we measure our tensile properties in these three principal directions, right, our tensile properties are greatest in the longitudinal direction, where we're pulling along these stringers. Going to be the worst in the short transverse direction because we're pulling, right? Remember, these things, this is a 2D slice through a 3D structure, right? These are sort of like sheets of these intermetallics, and we're now pulling along them, right? We're pulling normal to those sheets, I mean, right? So those are going to give us the worst properties because we're stressing normal to these stringers, right? And just an example of the properties, right? 7075, right? Aluminum, zinc, magnesium, copper alloy, right? The yield stress longitudinal is 50 to 75 MPa higher than in the short transverse direction, right? The ductility is reduced by a factor of 2 along the transverse direction and the short direction, okay? Grain size, remember our Hall Petch, our KY is quite small, right? And this is very low compared to iron alloys. Remember, this is BCC, right? But we do see some strengthening effect. But unlike some other alloy systems with aluminum, we can generate very fine grain sizes and retain very small grain sizes. So we can reduce the grains by over 2 orders of magnitude, right? And even though the Hall Petch effect is very small, this big reduction in grain size can give us an almost 3 times effect in strengthening, going from a yield strength of 20 MPa in commercial pure aluminum to 56 MPa, right? So recovery and recrystallization. In very pure aluminum, recovery and recrystallization can occur at very low temperatures, right? So in pure aluminum and commercial purity aluminum alloys, right, strain hardening is not an effective method of raising the strength of this material, right? As the purity decreases, though, grain growth becomes inhibited by the solute drag and pinning, right? Because of these impurities, which are dang near impossible to get out, right? They're always there. And they give us, we can leverage them to get fine intermetallics that are going to give us grain growth or inhibit grain growth, right? So small variations in purity can give us very different sets of properties and very significant differences in the microstructure of aluminum, even though if it's processed the same way, right? Toughness. We really need to be concerned with toughness, right? Remember, strength and toughness tend to have opposite trends. Things that increase the strength of our material tend to decrease its toughness, right? Especially in the presence of cracks and flaws, our toughness becomes a very, very important factor, right? Cracking in aluminum is ductile, so we have a ductile fracture mode, right? So we have growth and coalescence of microvoids nucleated at a crack, right? But we can short circuit this because we can nucleate cracks at these coarse intermetallics, right? And remember, the surface energy, if we want it to be good at grain boundary pinning, right, it needs to have a low surface energy. I said that backwards. Right? The low surface energy helps in this case. But so we get decohesion at we can get potential decohesion at this interface, right? So the distribution of the particles, right? The cracks will tend to go from particle to particle to particle, right? We got local strain concentrations. This is going to accelerate our void coalescence, right? When grain sizes are small, void coalescence happens to be along the grain boundaries, right? So all of the mechanisms that we talked about to increase our strength is going to wreak havoc with our toughness. Okay. We want to reduce the level of iron and silicon, Ri, right? Well, we get these submicron particles. The good is it suppresses recrystallization and inhibits grain growth, right? And that our fine grain structure, right, favors an intragranular failure mode. The bad is these particles nucleate microvoids by decohesion, right? And these microvoids can then link up and give us failure, right? However, right, you see here that our fracture toughness for fine unrecrystallized grains is higher, much, much higher than for large equiax grains. Okay. Fine precipitates from aging, right? Their presence tends to inhibit deformation and increases toughness, right? Although they localize slip, right? Remember that as the particles are cut, right? That can give us stress concentrations in front of advancing crack, right? Not a good thing, right? And we are going to stop there. Coming up on Friday, we'll talk about fatigue properties and some examples, the effects of strain hardening, right? The microstructure features, substructure hardening, texture, and then we'll go on to some specific alloy systems. So hopefully we'll get started on those by Friday.